So I will start. So hello everyone. Very welcome to the Computational Genetics Discussion Group seminar. And today I'm very pleased to invite Dr. Maya Hiltpold. And before I would like to give an introduction about her. So she did her master's in agricultural sciences, especially specializing in animal sciences from ETH Zurich, followed by the doctoral thesis in genetic characterization of impaired semen quality and insemination success in brown Swiss. In that time, I had pleasure to work with her for the 4 years. And after that, she moved to INRAE, and currently she's working on genotype by environmental interaction of mother-lamb energy allocation trade-off. So very welcome, Dr. Maya, and I give floor to you to start the presentation. Thank you.
Okay, thank you, Minu. So then I will start. I first will give you an overview how I will introduce you to genotype by environment interactions of the mother-lamb energy allocation trade-offs. So first I will explain you the allocation problem and potential trade-offs. Then I will give you an overview on our model. Then show you how we use the model to evaluate the U-Life performance. Then we check the effects on the U-Life performance, and then I will give you a conclusion and outlook. So generally, body reserves change depending on the animal's need. And in ruminants, or especially in female ruminants, the capacity to mobilize and reconstitute body reserves is a key physiological mechanism. So in reproducing ewes, you will have, depending also on pasture growth and their physiological state, there will be changes in body reserves. So for example, if we have seasonal pasture growth with a peak in spring, and then like a reduction in summer and another increase in autumn, we'll here have ewes lambing, and then they will be weaning the lambs here. So in this time, they will mobilize body reserves and we lose them. And this is a period of high requirement, or when there also can be mobilizing more when there is low feed availability. And contrary, they will reconstitute the body reserves in periods of lower requirement and high feed availability. It has been shown that the gain and the loss of the body weight, or also the body condition score, so the body reserves, they are heritable traits, not very high, but they're heritable. And it also has been shown that different profiles of the body weight and the body condition score dynamics in the same environment exist. So the question is, if we have a ewe that changes more, we can have ewes that change more in body reserves and so that change less, for example. When it comes about to the resource allocation problem, there is the fact that animals have limited nutrient resources to spend, and this is limited because of the intake capacity, the feed nutrient density, and the feed availability. So all those factors may then give the amount of nutrients or energy that can be used. And then it's very important to state that the energy intake is equal to the energy expenditure and the change in reserves. So you can't create something out of nothing. When the animal then allocates the nutrients to body functions, we can differentiate between different functions. For example, somatic homeostasis, activity, growth, immunity, pregnancy, lactation, or reserves. And those body reserves, they're very relevant in terms as a buffer capacity. But then the question is, do we need, so we need a piggy bank or a sheepy bank in this case, but do we need a small one or do we need a big one? What is better? What is more adapted? And then, so we come to the fact that we could have different strategies, different levels of reserves, and which of those body reserve changes or strategies is adapted, and is there a trade-off between the ewe and the lamb production? So which strategy is adapted? We can have ewes that invest a lot into their lambs and produce many lambs, or have fast-growing lambs. We can have ewes that invest more into their longevity and are a bit more careful when it comes to having lambs. Is there a trade-off when we look at the lifetime performance? And here I define lifetime performance as the number of lambs the ewe is producing in her life. So this is a multiplication by the lambs times the longevity of the ewe. So we built a model. This is a mechanistic energy allocation model. And still we have the fact that we can't produce energy out of nothing. So we can just spend it to different functions. So we start with the inputs. We have different energy density and different available quantity. And then our ewe is able to have, she will have a desired intake, how much she wants to eat. But there's also a limit in the intake capacity, because the rumen volume, you can imagine the rumen volume just has a certain limit. Then with this energy that is available from the intake, the ewe can spend it to different functions. For example, to growth, which then translates into protein in the model, or to reserves, which are lipid and protein reserves, that then as well can be mobilized again for maintenance, or to maintenance because, let's say, our sheep needs to stay alive. And then for female reproduction, the ewe can invest energy into pregnancy and lactation, which then translates into the gravid uterus and the number of lambs born and the birth weight of the lambs. And for lactation into milk. And then because the lambs in the model are directly linked to the ewe, this translates into the lamb energy intake and into lamb growth. When it comes to the ewe, we will have different body mass and body fatness resulting from this model. So we can have different profiles. For the reproduction, I built a submodel, which is hierarchical. So there are conditions that the ewe needs to fulfill to be cycling. So it needs to be female, mature enough, should not be pregnant or lactating, be above a minimum threshold for the body condition score. And there are also factors as day length and day length variation, which can be used to introduce a more or less seasonal cycling ewe. So once our ewe is cycling, then there's a probability of being in estrus, being on the day of the cycle. And then at some point, an estrus will happen. And at this estrus, there is a ovulation happening. There's a random sampling of the number of ovulations, depending on the ovulation rate potential, the maturity, body condition score, and the body condition score change in the last 6 weeks. This is kind of a flushing effect. Then after the ovulation, when I tell the model that there is a ram present, then there's a probability of conception, which then depends on the body condition score and the number of fertilized eggs. And if this then results in a number of embryos which is greater than 0, so at least 1, this translates into pregnancy. And if not, if all of those stages where it fails, we actually go back to the being cycling, and the ewe will be in estrus again if she's still cycling. When it then comes to the allocation to the offspring mediates the lamb and the ewe survival. So we have the allocation to pregnancy and the number of lambs that finally define the lamb birth weight and the lamb survival at birth. And if the lamb has had a high birth weight and the lamb died during the birth, so from hypothetical dysostia, then the ewe also has the probability of dying at birth. So I will show you on this graph. There's a function, a probability of dying for the lamb, depending on the birth weight that you have, that is here on the x-axis. And there's an optimum where the probability of survival is the highest. And below, there's the probability of dying because of hypothermia and starvation. And above, there's the probability of dying because of dystocia. And for the ewes, the probability of dying increases actually, or the probability of surviving decreases when the lamb has been very heavy. Additionally, there's every day a sampling if the animal dies or not, and this is dependent on the body fat reserve level, the maturity, and the age. We then used our model to explore the effects of, on one hand, the feed, which is here defined in terms of energy supply. So here I call it environment, and of the factors that define the priority between those functions, like which define the responses of the animal. Here call it genotype. It's for sure not entirely genotype. It's more like the animal type or the animal. But for simplicity, I will call it genotype in this presentation. And then we can also have the interaction of the environment and the genotype, which then have together the effect on the output. I defined two feed scenarios, so two environments. We have a favorable one and an unfavorable one. So in general, you can imagine the favorable one as like the green grassland and the unfavorable one as the one which is not so green. So in the favorable one, we have good pasture grow and forage. There is favorable grass growth and regrowth. So we have intensive grassland management. And when we look here, it stays also pretty high, the feed quality during summer. And we have some cereals around lambing, which increase the feed energy content a bit more. In the unfavorable one, we have also good spring pasture, but then it declines. And then there is very low forage quality or pasture quality during summer because of an assumed summer drought. And then only then in autumn it will regrow. And during winter feeding, which is here, we have lower feed quality in the unfavorable one because we conserved older feed. And there is no complementation with cereals around lambing. So the mating takes place in this time of the year, which then translates into this lambing period in spring. And then depending on the lambing date, the ewes have this suckling period, which is always the same length, or this one in late lambing. So as you can see in the unfavorable scenario, the ewes, they crash quite into an energy density shortage at the end of the suckling period. When it comes to the input parameters which characterize more the animal, there are many, many input parameters, and they control the survival probability, the acquisition, the allocation, the energy conversion, different body components, conversion, and also the reproduction. And for some of them, it makes sense to consider them constant. And for others, it makes sense to consider them variable. So what we did, we used 22 parameters, which are potentially variable, which are potentially relevant to be considered variable. And I put them into a sensitivity analysis in the two environments. And for this, I used the Morris design with 4 levels and the 22 parameters, and then with 120 repetitions. And this then gives a total of 2,760 simulations in each environment. And you can imagine this Morris design is chosen to well cover the parameter space that you kind of still have good coverage of the space and of many combinations, while heavily reducing the number of simulations you need. Because if you would do a full design, you would have a lot of simulations and it would be very computationally intensive. So this is a method to reduce this. Within one simulation, so within one set of input parameters, there were always 20 U's, which are of the same input parameter. So we have 20 clones in each simulation. And those clones, they produce lambs of the same input parameter. So they produce, again, clones for now. And this is relevant that I take 20 U's, because with the 20 U's, I can then calculate a mean out of 20 U's. So there is a bit less of the random sampling, which has an effect. So what we did then, we were looking at traits, like the model outputs. There are U traits, which like the body weight, the body condition score, the feed intake, and the longevity. How many parities, how many years the ewe is living. There are lamb production traits like the number of lambs born, the number of lambs weaned, the lamb survival at birth, the lamb birth weight, the lamb body weight at older ages, the milk intake, the growth rate from birth to 42 days or to weaning, to survival from birth to weaning, and so on. What we choose to look at was the life performance of the ewe, and we defined it to be the total number of lambs weaned during the life. And we here use this abbreviation for you to keep track. So when we look at the difference between environments, we see that in the unfavorable one, the ewes weaned a mean of only 6.1 lambs, and in the favorable one, a mean of 11.1 lambs. So this is clearly different. And when I show you the graph of the performance in the favorable environment and in the unfavorable environment, then each of those points is actually a genotype, which has been subjected to the two environments. And the correlation is not very high, it's just 0.6. And we will now check why the correlation is rather low. So for this, we use the sensitivity analysis because with this Morris design, we can also calculate indices which help us to check which of those input parameters have which effect size. So on the x-axis, we have the mu star, which is the linear effect size. And on the y-axis, there's the sigma. This is the non-linear and interaction effect size, so both of them. So in both environments, the ovulation rate potential was important, had a large effect. And in both, the target body fat reserve level was also important. And then we have here the basal intake level, so how much the animal eats. And also the degree of control of the body reserve level. So if the animal gets fatter, it will eat less. How steep this response is. So let's now have a closer look at the ovulation rate potential. We have, this is the prolificacy potential, and it varies from 1.2, 2.1, 3.1 to 4 expected ovulations. So when we see here that in the unfavorable environment, the prolificacy potential is only weakly expressed. So even if we increase the number of ovulations, the number of weaned lambs doesn't increase a lot. Whereas in the favorable environment, there's a clear increase. So I will show you the same graph that I showed you before now with the colors. And this explains why there is such a large difference between the two environments. And we see here that we have some different clusters depending on the ovulation rate potential. So I show them to you separate. And we see that for the low ovulation rate potential, the correlation was actually even lower between the two environments. So not the same animals had a high number of lambs compared to in the two environments. whereas for the high ovulation rate potential, the correlation was much bigger. Well, so why those ewes weaned less lambs despite the fact they were more prolific? Well, the problem was that the prolific ewes, they have poor lamb survival, especially in the unfavorable environment. So in general, the lamb survival was much less in the unfavorable environment compared to the favorable environment. And I will now show you the effect of the ovulation rate potential. So we can clearly see that the lamb survival at birth decreases when we increase the ovulation rate. And that this is actually worse in the primiparous ewes and in the unfavorable environment. And in a favorable, like the two lower prolificity potentials, they're almost equal. So we have the problem that prolific ewes, they don't necessarily produce lambs who survive. So far we have seen that the number of lambs weaned in the life of the ewe is theoretically positively influenced by the ovulation rate potential, but there is also a negative effect of the ovulation rate potential when it gets too high on lamb survival, and only if the lambs survive, they can be weaned, which also sounds very logical, but you still have to kind of find this out when you look at such things. And now, when it comes to ewe longevity, what would be the effect of increasing the ewe longevity? Is it positive, negative? Let's have a look at this. So in general, we can say that the ewe longevity limits the number of lambs during a life. So on the x-axis, we have the mean number of parities the ewes reach, and on the y-axis, still the number of lambs weaned. There's a clear effect of the ovulation rate potential, but we can see that in general, the ewe needs to also live long to reach higher number of lambs weaned. And this is the same graph splitted for the different ovulation rate potentials. So when we look at the low ovulation rate potential, then the correlation is very high. So we need to kind of improve the longevity of the ewe to wean more lambs. It gets a little bit less. And then when it comes to the very prolific ewes, then we also will find ewes who continue living, but they still don't really wean lambs. So this means all those lambs are dying. When we now check the ewe longevity, in general, it's lower in the unfavorable environment. So it's only 4.3 parities versus 6.3 parities in the favorable one. And what now influences the ewe longevity? This is again a sensitivity analysis, but here on the number of parities. So there is the target body fat reserve level, which plays again a role, and the ovulation rate potential. And especially in the favorable environment, the basal intake level. And now as a reminder, I will show you the same graph I showed you before for the ewe life performance. And here we kind of had the same input factors which were important. When we now check the effect of the target body fat reserve level on the ewe longevity, then we clearly see that the higher the target body fat reserve level is, the ewes are living longer, and this is more pronounced in the unfavorable environment than in the favorable one, but as well in the favorable one, they will live longer, mean. And also when it comes to the basal feed intake, so how much the animal eats, there's also positive effects. It kind of makes sense that the animals who eat more, they have more to spend So they have more to allocate to different functions. So we have seen that concerning the ewe life performance, the ewe longevity also positively influences the number of lambs weaned. And this is that the ewe longevity is positively influenced by the higher body fat reserve level and the higher feed intake. So when we now focus on the ewe life performance, what are the leverage effects? So there is the prolificacy, which is the potential prolificacy versus the realized one, because if there is just a high potential, but it's not realized, it's kind of useless. And this is characterized by the ovulation rate potential and then also the lamb survival. When it comes to ewe longevity, it's very important to consider that the prolific ewe also needs to be able to sustain this prolificacy, because if she's dying or if the animals just have a very low birth weight and they're dying, it's not really worth to be prolific. So in general, we can say that the ewe needs to balance her condition and her investment to the lambs. And this is also, we have effects that act on this, like the intake level and the reserve level. When we now link this to the animal breeding, then it's, in animal breeding, we would like to select the best and select the best one in terms of what we consider a performance. So there are effects of the environment and the genotype on the performance, as I have shown you. So basically, we have a balance. So we need to balance between the ewe and the lambs, and we will balance this with different animals, with different genetic strategies. And then we can put our resources into we can allocate them more towards the ewe or more towards the lamb. So this means we have the genotype and the environment that act both individually on the output, on the performance, and they also act together on the performance. And it's even more interesting if we look at this life performance, because there's the temporal aspect in it. So when we now look at genotype by environment interactions, we can do the ranking within each environment. So we'll have the effect of the genotype, the effect of the animal. So we still here, the trait is the number of lambs weaned per ewe. And on the left here, we have the favorable environment. And here we have the unfavorable environment. And actually what I did, I just used the quantiles. So here we have 10% quantiles. So on the top, you have the 10% best performances. And on the back, here at the bottom, we have the 10% worst performances. And what does it now mean? I mean, you already see, sorry, again, here the colors are the different ovulation rate potentials. And we already see that maybe those colors don't necessarily match exactly those colors here. But how do they match? Do we have changes in ranking or what happens? And actually, if we then put them together, you will see that some of them, they stay, so they keep their rank, which we will consider there is no interaction, but they can also change rank and they actually can lose or they can gain rank. Everything is possible. And the same is true when it comes to the target body fat reserve level and the basal intake. So those is the same graph, just with different colors based on different input factors. And you will see also here the animals that tend to have higher reserves and those that tend to eat more, they classify more often among the 10% best. So those 10% best, we have actually different input parameter combinations. So we can have different genotypes, different animal types, we can lead to the same ranking result. So now I will give you a take-home message. Generally, our model is capable to simulate the response of a genotype in a given environment, in a given feed resource environment, still a limited kind of environment type. So we have the effect of the environment, we have the effect of the animal, or the effect of the genotype, and we will also have the genotype by environmental interaction. Then the big question is which many traits exist and on which traits should we focus? And we decided to look at the ewe life performance because it's more interesting as we can simulate the entire life of the ewe with our model. But for sure, other traits are linked, and it might also be interesting to look at other traits and check if there are trade-offs between the traits. We use the Morris sensitivity method as a tool to identify the most important input parameters and also as a help to be able to choose which we should consider variable. And when it comes to the question if there is a compromise between the ewes and the lambs, I guess we can say there is a compromise because there is a need to balance the allocation between the ewe and the lambs. And now I will even give you a conclusion and outlook. So our model can create clones that lend support for genotype by environment interactions. However, the model critically depends on the parameter choice and assumptions, what it will give as an output. And what we would like to do is, with help of the model, can we find a super ewe that performs the best? And is this super ewe that performs the best, is it the same in both environments or is it different? And for this, we'd like to do some optimization. And it's also possible to do the optimization on more than one trait, which potentially have a trade-off. And then there's another question, what key aspects have we missed if this super ewe cannot actually exists? There are also trade-offs which are not about energy allocations, which we don't have in the model. And what we'd also like to do is to introduce inheritance, because in real life, the lambs are not clones of the ewes, and this would make the thing a bit more interesting. And with this, I thank you for your attention. And I also thank the adapter partners which contributed to this project. Thank you.
Thank you, Maya, for this really clear and nice presentation. So if you have questions online, you can either raise your hand or and unmute yourself, or just put it in the chat. And you can see here. And if there's 3 people who made it today to the Roslyn of question, you can also ask a question now. Yes, Andrea, can you unmute yourself?
Yeah, can you hear me okay?
Yes, you can.
Okay, brilliant. Thanks a lot, Maya, for this great presentation. I know Frederick has been here, so I am familiar with these models a bit.
A bit. Okay.
A bit. So I was wondering, because it's really interesting, I can really see the power of, exploring genotype by environment interactions. Can you maybe guide us a little, talk us through a bit how you represented the genotype in this model now? So yeah, yes, maybe just what was how did you classify a specific genotype?
Well, we not really classify the genotypes, but we have.
How did you define a genotype? Yeah.
I mean, we have different input parameters. And I kind of just say that different input parameter combinations, they will result in being my genotype.
Yeah, so I was wondering, because you have so many input parameters, so just to refine my question a bit, like did you classify the genotype into a highly productive one and a low productive, and then were your parameters kind of correlated? Did you set a certain cluster of parameters to a certain value to say this is my production?
I mean, I tried to define like a minimum and a maximum of the of each parameter, which was kind of, for sure, kind of arbitrary, because I could not explore all parameter combinations and then what kind of effect does it have, like manually. It's just not possible. So what I did, I just kept the others constant and then moved around like one parameter to kind of somehow set the minimum maximum, because my mathematician, so like Ronan Trépeau is the mathematician, he said, you need to define the minimum and the maximum. I was like, okay, I will do this work. And then basically with this sensitivity analysis, we first, like of the first time we put them together and were like letting them act together. But yeah.
Okay. Yeah. So there's no defined clusters, classification, a highly prolific type compared to, it's just you had different combinations.
So far, no.
Okay. And again, because you can you just remind, because so you had 20 clones always. So what was random in this? Where did you draw random samples from that you get? Why did you make 20 replicates for each parameter?
So there is random sampling there's random sampling actually in the, there's random sampling in the reproduction part. And there is also, so we have all those reproduction events, there is random sampling.
Okay.
Like binomial sampling.
Okay.
And there's then also random sampling in a survival part.
Of course, okay.
Which,
because otherwise it's fully deterministic model, right?
Otherwise it's fully deterministic, but in the reproduction part and in the survival part, it's random.
Yeah, of course.
Which with probabilities that are adjusted according to the current state of the sheep, like the body condition score.
Okay.
Then it has when it gets too thin, the probability of dying will increase.
Okay.
And when it stays a long time like thin, then it has had many chances to be sampled, you die.
Okay. So now I understand the model a bit better. Sorry, can I ask one more question? I don't know how many questions everybody else has.
Yeah, sure. Ask another question, Andrea.
Okay. Because the reason I'm asking so where do you see at the moment the usefulness of this model? So it's a very complex model. I think you have demonstrated that you can explore the interaction between the genotype and the environment, and it often leads to very unpredictable results that would be really hard to predict otherwise. But because you have a mechanistic models where all these processes work together, you can actually get these predictions. So do you see, what's the power of this model? Do you see it's more to demonstrate how genotype by environment interactions can occur? Or do you think it actually has a real, could that be moved forward to a real predictive model for animals that actually exist, and you can calibrate the parameters, you can estimate parameter values for these animals and then explore how they would do in different environments? How do you see that?
I mean, calibrating the model would always be very nice, but the problem is a bit the lack of data. Because, for example, if I put my model sheep on a pasture, already the intake, how much does it really eat? It's not easy to get really a lot of data on this. And so this would be nice. I think what it's able to show right now is that you cannot necessarily say, I select my animals in the environment of now, which is maybe good. And they will be the same ones that will be good in a more constrained environment, in a different environment.
So do you see any predictive power that could come out there?
So I would say it's interesting to define kind of different breeding goals depending on different environments. There is some predictive power, and and also what kind of might be the limits. If you still always go into more of something, there might be some limits. But again, it's very difficult because I mean, I have assumptions on my parameters and assumptions in the model, and if those are wrong, the prediction will also be very wrong at some point.
Yeah, but I think one shouldn't be too shy because the alternative is regression models, and we know they are wrong when the environment changes. So this is better. I would always
that's
say,
the
okay,
thing.
you have a lot
I
of
mean, you
assumptions,
just
but
can
yeah.
with statistical data, you can just look at data you have.
Exactly. It's
And
even harder to predict.
there's limitations in what you have.
Mhm.
And here we try to put all the knowledge we have now into a biological concept, and we try to predict then things we don't know yet.
Yeah, I would agree. I mean, here you don't know the parameter values, but you know the processes, or you have a good idea of the processes. In the alternative type of models, right? You have sort of statistical linear regression or something. You don't know the
Yes.
processes, but you may fit parameter values, but because you don't know the processes, you don't know how they play, what role they play in different environments. So there's always a bad, a pro and a con for different types. That's why I was asking how you see where your model fits, because I think it's quite
I mean, one direction we also want to go is, I mean, right now it's a suckling sheep. We want to make a dairy sheep out of it, and there's a PhD student who should use this model in her thesis to kind of evaluate different farming systems. And then also the idea is to do some genetic selection, and then also after the selection, run again this model to predict the performance.
Nice. Nice. Yeah. I better shut up. I find it very interesting. Thanks a lot.
Thank you, Andrea.
Great presentation, Maya. Oh, yeah. Sorry, trying to. Okay. Nicola is here. Maybe she could ask first.
Okay. Did that work?
She said she's trying to unmute.
Yeah, so I try to, should be able to mute people.
Ask to start the video, maybe. It might work.
Well, if you cannot unmute, you can maybe type your question in the chat, and meanwhile, Mino, you can ask your question.
Yeah, it was a bit difficult to understand, being not working in any kind of mechanistic modeling, but more of a general question. So in your okay, I have two questions. So first, I will start with the last one. So in your top 10% and top 10 below the worst performing 10% for all three traits, you all have both for worse environment and for favorable and unfavorable environment. You both have same, like that nice plot you showed. So if so, just as a breeder question, if I have to say, I should just use the top 5%. I could choose them to select the animals because they would be good in both environment. Did I understand it right or wrong?
Yes, I mean, you could choose the animals which don't change ranking, yes, in both environments, and which are among the best. Yes, you could do this.
Yeah. But as you said, the interaction of these traits have not been taken into account in these model, right? Because
How
you
do you
have
mean
pretty, okay.
I mean, this is just based on one trait, right? So
Oh,
like the
okay.
total number of lambs. So I just go for quantity.
Oh, you just go for the quantity. Okay.
I mean, just for simplicity, I chose this for now.
For now, okay. Yeah, I'm just still trying to. So when you choose the 21 parameters and you said you keep some constant and some on range.
Yes.
So I was wondering, does those parameter have any kind of interaction between them? Just based on the name, it looks like they might have
The
in
one,
a real life
the
data
one
set.
I'm changing.
Yes, the 21 parameters you have.
Yeah. They have some interaction. I mean,
they might have some interaction.
Yeah. I mean, if you just look at this, for example, I'm showing you again this one.
Yeah.
I mean, we can't distinguish with this method. We can't distinguish if it's non-linear interaction, but I mean, there is some interaction. Otherwise, they would all be here at 0, right?
Okay.
There is some non-linearity in interaction between when you change one parameter and you change the other as well.
Yeah.
They will interact.
Okay. Oh, that's
Yes.
amazing if they are a model already take into account, which
They will interact. So you will have actually that's what I was trying to show here with the with this graph. So you will have a combination of input parameters which give you the performance, which give you the genotype.
Okay. Yeah,
The question is more behind if you have input parameters and we would consider them genetic, do we consider them to be uncorrelated?
Yeah.
Or do we consider them to be correlated? And this we don't know.
Okay. I have more question, but I'll ask you personally, but
Okay.
there is more question online.
So Nicola, if you worked out how to unmute yourself, you can now unmute and
Thank you.
we'll
Yeah, I'd realised that it was asking me was it okay that it was recording, and I hadn't pressed OK, so I couldn't use my other controls. So it was just about voluntary culling policies. So do you put assumptions into the model about whether ewes are allowed to stay in the flock in subsequent years, because it looked like they could be of a high parity but have produced very few lambs to weaning, whereas
Yes,
probably in practice they would have been culled out the flock, or if they had a
Exactly.
particularly low body
So-
condition score or something.
So far, I didn't introduce any culling for the ewes. So the ewes just live as long as they live in the model. Because I was
Okay.
just wanted to look
Yeah.
at what happens if there is kind of no human intervention on this. But they will die if they get too thin, for example.
Right.
So, but I mean, you're right. I mean, if I would show you, I mean, in reality, those ewes that are kind of not producing anything. I'm sorry, I need to put the pointer. Those ewes that are producing like no lambs but living a long time, in reality they would not exist.
Yeah.
I mean, on one hand they would get extinct because they don't have lambs and they don't pass on their genes, and on the other hand they would be culled.
Okay. Thanks.
But so far it was very simple, so they just live as long as they can, and or until the model the simulation ends, which is like 10 years.
Okay, thank you. If there is no more, well, if you have a last question, maybe you can mute now. And if there is no more question, we can thank Maya again for the talk today. Thank you all for attending, and we'll see you in the next CGDG. We don't know when it is. Thank you all. Thanks, Maya.
Thank you.
Oh, there is more. Okay.
Nothing, it's just, yeah, congratulations and stuff like that. I should